Good morning to everyone. I'm Gianni Pecora, and I'm here to present the progress of the last year. So, as you all know, operational electric propulsion satellites are really popular in the last years. So there are more than 7,000 satellites in orbit with electric propulsion. The all-effect thruster have more than 1,000 seconds of ISP, and it's possible to do a GTO to GEO transfer all electric in more or less 6 months. But onboard guidance must be closed loop, lightweight, and also certifiable. I'm an industrial PhD in Gianni space, and all the things that I'm developing are integrated in i360. That is mission analysis tool. And the goal of the last month was to establish an asymptotic Lyapunov stability for state-dependent QLO scheduling, and also coupling everything with a more realistic digital twin, like adding power or also IDCS. What we have today? So there is the QLO, that is a Lyapunov function from Petropoulos. So it's a control law that has static weights that can be tuned with, for example, a generic algorithm, but they are mission specific and not adaptive. With OLT, the weights begin to be state dependent, so more adaptive, but I saw two different gaps. So there is no formal asymptotic stability for state-dependent QLO weight scheduling, and also the adaptive guidance is decoupling from power dynamics, and also from IDCS. So there is not a really digital twin of the satellite. So talking about the QLO is, as I said, a Lyapunov function that is the square sum of the error or the orbital elements normalized by the maximum civil element rate, and you can derive the optimal thrust like minus C, where C is the gradient of the QLO, so it tells you which are the more urgent orbital element to be changed, and then you have also the gas variational matrix. But as you can see, the derivative of this QLO is always minus than 0, so you have asymptotic convergence when the weights are constant. But what happens when the weights are changing by time? You have another term, so you cannot guarantee Lyapunov stability. In order to have Lyapunov function, this function needs to be positive defined, and also the derivative needs to be minor than 0 log trajectories. So the idea is to decouple the Lyapunov function from the control law. So you have a Lyapunov candidate that is the QLO with frozen weights, and then the control is changing the weights during time. In order to have stability, the derivative needs to be minor than 0. And it happens to be just the inner product of CV and SynQ. So what does it mean? It means that there is a limit of the weights that you can choose in order to have stability. And you can also have, you can see also there is a delta, that is the perturbation decomposition. So it's the difference between the dynamic weight and the frozen weight. And the difference between CQ and CV is linear in delta between a perturbation matrix. But the real question is, how far can I change the weights in order to have stability? So we create a theorem that is based on the thrust effectivity, and it's based on the thrust effectivity and the spectral maximum spectral norm of the matrix M that I was showing before. And basically, what he's saying is that there is a delta star. That is, so it's the difference between the dynamic weights and the frozen weight, below which you can always, you will always be safe, you will always have stability. And this is a function of the threshold, so the threshold, the thrust effectivity threshold. So the thrust effectivity will be a gauge for both for the propellant efficiency and also for the Lyapunov stability. But This theorem is really strict, so what I'm really doing is really conservative. So what I'm really doing during runtime is enforcing the worst case alignment during runtime. And then if the alignment it's not respected, so if there is no stability, we have a bisection projection in order to go in a safe space of the weights. But the question is are we losing performance? I did a benchmark and I saw that we are losing less of the 1% of the entire propagation doing this. So how are we changing the weights? We are using reinforcement learning, in particular the PPO, proximal policy optimization. And we have a state that is with orbital elements. Then the action are the weights of the QLO and the trust effectivity threshold. And then there is a reward that is the most difficult to be shaped. And it depends on if we are talking about a scenario that is time optimal or mass optimal. But in both cases, we are using the frozen Lyapunov candidate and not the one that is reshaping by time with the weights that are changing during time. But the important thing is that inside the training, we are adding stability. So we are projecting, if it's necessary, the dynamic weights inside the safe space of the weights. So the agent never trains on unstable trajectories. On the other way, we are adding also power to the environment. So in the benchmark that I did, I considered different environment with eclipse, without eclipse, and also with power. And all of them have more or less the same operational machine that is composed by an operation where you are thrusting using the QLO, and the other one where you are charging. And you are passing from one to another with the state of charge of the battery and with the trust effectivity threshold. But when we are considering power, we have two different strategies. We have one where the power is it can be maximum power or zero, and the other one is where we are changing power during time. So you can see here a plot of power with mass flow rate. And we have two different curves. One is the one where the flow rate is constant. So when the time is optimal, we are moving on this curve based on the power. And the other one is an ISO efficiency power, and we are moving in this one when we are doing the mass optimal strategy. And both of them, in both of them, we are considering for changing the power a function of the state of charge of the battery. So here I'm going to show you some results. What I want to highlight here is that I did the training in different environments, so with eclipse, without eclipse, with power, and with variable power. And I had you can see that when you are training in an environment and then you are using the same one without retraining in another environment, we saw that there is stability and robustness because we still have great results anyway without retraining. And also you can see that we have better results using the variable power respect with the one, of course, that is constant. But better results for the variable power are also in the, okay, so I forgot to say that it's a GTO, in this case, it's an example of GTO to geo transfer. And this, in this case, is the mass optimal one. And with the variable power, we are saving like more or less 1 kilogram of propellant. And also in this case, the stability works. And as I said, we are training everything with with the stability in the loop. In this plot, you can see that the row policy is not stable. We are going below the stability, but with the runtime enforcement of the we are projecting the weights in a safe space. So you can see that it's always stable, always stable. So all all the training are done with stability, with Lyapunov stability. And here I want to show you some of the next steps that we are trying to achieve. So we are already develop the entire ADCS part, and we are in the part of the validation. So we are validating against other tools like Basilisk or Fortitude. And other possible extension of this work is extend the stability to perturbation. And yeah, in this slide you can see some of my achievements, and in particular I'm about to submit to Acta Astronautica my first paper in the next days, and we are preparing the second one. Thank you.